we're sort of going to see what we had seen in 3100, right? So in 3100, we first saw lambda calculus without types, and then we saw simply type lambda calculus, right? We studied a lot of these things, a lot of the semantics you can even study without types, right? Because you can still do lots of interesting things. There is Turing completeness, there is big step, small step semantics. All of that is going to be there. But what we're going to study formally, right, compared to the study of simply type lambda calculus from 3100, is that we will actually formalize it in core. But we also had this notion of type safety, right? We said, oh, there is this notion of type safety. If you have types, well-typed programs do not go wrong. This is what we have in OCaml as well, right? It's a beautiful concept, right? So if your program type checks, then your program does not have memory errors, according to I mean, it doesn't go wrong, by which it doesn't have any memory errors, is what OCaml provides you. You can also extend it to what Rust provides, right? Type system is sort of not just one property, it's sort of whole gamut of properties that are encoded statically, where before even running the program, you sort of do some analysis, right? And Rust provides this as well. Rust goes much further. Rust gives you data race freedom, right? If your program is type checks in Rust, if your program is a well-typed Rust program, then your program does not have any data races, which is excellent, right? So when you write parallel programs, that's like a very, very interesting property. It also provides memory safety, even without garbage collection. So all of these are sort of building upon some principle, right? So there's some operational notion, operational semantics for the underlying language. What the language, what does it mean to execute the program, right? And you sort of construct a subset of the possible programs that are allowed to execute, right? And that is done through types. So I mean, the whole concept can be sort of classified as getting safety through types. And simply type lambda calculus is perhaps the simplest form where we can illustrate safety through types, right? We'll go to the entire extent, right? We will actually define what it means, formally define what is safety, and we will also show that simply type lambda calculus ensures this safety, right? So we'll see that in this lecture. So just like the previous lecture, right, where we had untyped lambda calculus, we have variables, the lambda abstractions and applications. In addition, we also introduce in expressions, we introduce these constants. Constants are just natural numbers, right? And just to make it more interesting, we also have additions on expressions. Obviously, the semantics is only defined. You can't add a lambda plus a lambda. You can only add natural numbers. I mean, that is what we are going to actually capture through types. But we have expression plus expression. That's a valid syntactic term, but not all of those expressions are well typed. Right? So we cannot add a lambda plus lambda. We can only add some expression that evaluates to a number with some other expression that evaluates to a number. Right? So those are the set of expressions that we have, and the values themselves are the lambda, right? The lambda abstraction and the constants. So they are also values. So this is the expression and the value language. Simply type lambda calculus adds types. We have what is known as simple types. Simple types are constructed with a natural number. A natural number is a simple type, and you have function types, right? And the function types are just arrow types that we know. So this could be arbitrarily complicated, right? I could have tau1, arrow tau2, arrow tau3, arrow tau4, and so on. But at the end of the day, each of these ground taus, right, are going to be natural numbers. So these functions, there are higher order functions, but the ground types are just the natural number types. Right? So that's the idea here. This is actually quite rich, right? You can define functions that take two natural numbers and take a higher order argument, which is also another complicated function, and may return another function as well. So we capture a lot of complexity just with this construction of types, right? So So that is our types, right? So this is the whole expression language for types. And we are going to say something about relating the expression to types, and that is what we see. And the reason why this is called simply typed lambda calculus is that we don't have, obviously, we don't have complex types. What are the complex types that we are talking about here? We don't have polymorphism, right? So in OCaml, an identity function will be alpha to alpha. Here, we don't have the expression. We don't have the ability to express polymorphic types, right? And that is the reason why we call it simply type. Um, anyway, so we are going to see simply type lambda calculus. And the dynamic semantics is mostly the same, right? Because we have uh, the expressions for additions, we also have evaluation context which tell how to evaluate the addition expression. So when you have an addition expression, first evaluate the left-hand side argument that reduces to a value, then go and evaluate the right-hand side, right? And once you've done all of the evaluation, you've gone all the way down and evaluated it, there are only two basic step rules. The first rule is the same as what we had seen earlier, which is the application, which is expressed by substituting v for x in e, right? And the other step rule, the basic step rule, is if both of these evaluate down to constants, n and m are constants here, and then this plus is the plus from the expression language, right? Then this evaluates to n plus m. Although you don't see it clearly, this plus is types it differently, and the meaning is that this plus is an expression language plus, and this is the actual interpretation. So the result of n plus m is just the result of adding n to m, right? So all we are saying here is if you see 5 plus 3, then in a single step it goes down to 8, right? That's the intention that we are capturing. Those are the only two low-level step relations. The higher level one is the evaluation context, right? If there is a sub-expression that you can evaluate using the step 0, then of course you just plug the result back into this evaluation context. So this is the same as what we had seen earlier. So that's the dynamic semantics. And now we have the static semantics, right? Static semantics is the type checking rule. So it tells you how to assign types to expressions. And in order to capture these types, right? So we have what is known as the evaluation context. And typically in programming languages literature, we use the evaluation context type as gamma, right? And anything that says gamma, this tilde symbol, some expression, colon, type is known as a typing judgment, right? So we call this whole thing a typing judgment. So it includes the typing environment, a tilde, some expression, colon, some types. And the way to sort of read this is under this typing judgment, right? This expression has this type, right? That's the reading. And typing judgment itself is just a map from variables to values. Sorry, variables to types. And the expectation is that we are going to give types for free variables here, right? And we are going to, under this assumption of types for free variables, we are going to assign a type for the expression. Right? And this is defined inductively over the expression language. We've seen all of this in 3100. I'm just repeating the same thing here. So for example, what is the type of a variable x, right? The type of the variable x is t, tau, if under the gamma, x has a binding to tau, right? So because it's a free variable, this expression, in this expression, x is a free variable. So you just look up the type for the x in gamma, that has to be tau. And if it is tau, then you can say that the type of this free variable x is tau. The type of constants, natural number constants is nat, right? And the type of expression e1 plus e2 is going to be nat. If under gamma, e1 has type nat and e2 has type nat, right? So this is sort of recursively calling type obligations on the sub-expressions, right? And the type of lambda xe, the abstraction is tau1 arrow tau2. If under the assumption that you extend the gamma, where you assign the type x to t1, sorry, t1 to x, right? If you extend the gamma with one extra assignment where you say the type of X is T1. Under this extended gamma, if the expression has type T2, then the original expression, which is lambda x dot t, has type T1 arrow T2. And what do you do for applications? The type of E1 applied to E2 is tau2, right? If E1 happens to be an arrow type, right, function type with tau1 arrow tau2 under the same gamma, and E2 has the type tau1. It matches the argument type of the function E1 here. And if it is so, you just apply, and the result type that you get is tau2. Right? So this is sort of well understood and straightforward, but it's nice to write it down formally, just so that we are going to manipulate all of this in Coq. So let's have a look at that. Okay, so now jumping to the Coq development. So we have a new module, STLC, simply type lambda calculus, right? So we have expressions with variables, constants, which are natural numbers, plus which is just a construction for E1 plus E2. Abstraction was earlier, and application was also there earlier. Right? That's the expression language. We also define what values are. Values are a subset of expressions, right? And there are only two values: the constants and abstractions. Right? And substitution remains the same. The only thing that we extend is how do you substitute within plus, right? This is a new. I mean, these two are new. Both of these are new. You can't substitute within a constant, so that remains the same. If you want to substitute in an expression which is E1 plus E2, then you recursively substitute within the sub-expressions, right? So that remains the same. Again, we have the restriction, so we don't, in order to not complicate substitutions, we assume that, yeah, so E1 is closed. The variable, the expression in which you substitute is always closed. This is the same as what we had earlier as well. Right? Again, this is sort of an orthogonal issue. Even without this issue, we can express all of the complexity. It doesn't matter here, but it sort of adds a lot of complexity. We ignore that here. And then you have the evaluation context. We have a whole is an evaluation context. We have two for +1, right? Two new evaluation context for +1, which is evaluation context on the left-hand side of the plus and right-hand side of the plus. And we have app1 and app2, which was there earlier. And as usual, we define how to plug the hole, right? We'll just look at one. So this plug +2 corresponds to, let me make it full screen so that I can go back and forth. So this plug +2 corresponds to this particular evaluation context. So what does it say here? So if you look at this one, the left-hand side is a value, right? And the right-hand side is an evaluation context. If it is so, then you can fill that hole in C with some expression, right? So here is plug +2. If you have a +2 expression with V1 and C, then you can plug the whole C with E, right? Assuming that if you plug C with E, the C with the Z, you get an E prime, and we assume that V1 is a value. So this is sort of restricting the sort of places where you can apply plug +2. Then you get the original expression, which is plus V1 E prime, right? So this is an evaluation context with a hole, and the hole is filled with E. And if you plug it, then the expression that you get is this one. But otherwise, the rest of the things are the same. So I'm going to skip that. And step 0, right? So step 0 has 2 reductions now, not just one. And the substitution is the same as what we had defined earlier, right? So we assume that V is a value and we have an abstraction here. Then if you want to reduce this application, then you simply perform substitution. Substitute V for X in E. Substitution is defined just earlier. And the other one is if you have an expression which is plus of const of n1 plus const of n2, then you reduce it to const of actually perform the arithmetic on natural numbers n1 plus n2. Okay, so that's also there. That is the step 0 function. The step rule corresponds to the rule here. How do you step the whole expression? If you can step 0 the sub expression, then you can step the whole expression, right? So e1 prime steps to e2 prime. If e1 prime is the expression that is obtained by plugging c with e1, right? And e2 prime is the expression that is obtained by plugging c with e2. And if you can step from e1 to e2 using the step 0 function, then you can big step, right? Sorry, not the big step, but actually step from e1 prime to e2 prime. Again, this is the same as what we had seen earlier. And as we had seen earlier, we can also build a transition system with this expression. So given an expression, the initial state is just the step function, right? And sorry, initial state is the given expression, and um, the stepper, the actual transition system transitions are just defined by the step rule. So our evaluation is deterministic, so there is no non-determinism here. So it is always going to there is not going to be any branching at all, right? Given a state, there is exactly one state that you can possibly go to, or your evaluation is already completed, right? So that's the expectation that we have. That's the transition system that we built. So okay, so those are all the things that we've seen in the previous lecture. Now we are going to encode the static semantics, right? And the thing with static semantics is it includes a gamma, and that's a map from variables to types, right? So first we have the type definition. Our types are natural numbers and function types, right? Nat is just a placeholder that just says that nat is a type, and we have function types with the domain and the range. So the argument type and the result type. So we have two types, and now we come to defining the typing relations here, right? So if you sort of stare at this, there are three components, right? The typing judgment, the environment that gives the types of free variables, the actual expression for which you are defining the type, and the type of that expression. So we capture it as an inductive that relates the typing judgment, the expression, and the type, right? And we call it hash type. So here is the typing judgment, which is the map from variables to types, the expression for which we are assigning the type and the type, and that's an inductive, right? So that's the way we are constructing it. And the way to read this is that let's just look at this one, right? X has the type under the evaluation context gamma. X has the type tau, right? If you look up x in gamma, then it is tau. So we have the same thing here. Under the evaluation context G, variable x has type t, sorry, t here, if you look up x in gamma and it is some t, right? So recall that this is the syntax for looking up in fmap, and that returns you an optional value, and the optional value that it returns here is some t. So it's a direct transliteration of what we've written in what we've typeset here to the Coq definition here. Let's just look at this rule. This is the interesting one, right? So so this is giving type for abstraction. So under the evaluation context gamma, the abstraction xe1 has the type function type t1 or t2 if you extend the gamma, right, with the type t1 for x, and in that extended gamma, if e1 has the type t2, then this whole thing holds, right? So this is the precondition for the body. So assume that the binder has type t1, and assuming that binder has type t1, if e1 has type t2, then the whole expression x arrow e1 has the type t1 arrow t2, right? So that's the entire one, and you can sort of follow along the rest of them as well. So okay, so we've defined it. We are going to use automation later. So I'm going to add all of these as hints to the auto tactic, right? So I call value, plug, step 0, step hash type as all of these constructors have been added to array to be resolved as proof steps for the auto tactic. So that's what I'm adding here. And then we add some notations. Just like earlier, I want to write lambda calculus terms in a neat fashion, but now I also have to write the types, right? And for the types, I use the minus minus greater than as the arrow for the type. So here are some examples. And then the other syntax is this funny looking syntax for plus. So this, when you see this plus, it is actually the plus constructor in our expression language. This is not the plus for the natural numbers, right? So what have I returned out here? I am writing an example 1 plus 1, where I say that the expression that you construct, which is 1 plus 1 in our language that we define, under an empty judgment, right, has the type natural number, right? So this is the proposition that I have written down. Of course, I need to show that this is true because this is just an inductive, right? And when you construct an inductive, you get a proposition. You have to actually show that this holds. You can show this just by calling eauto now, thanks to the fact that we've added all of these as proof steps, right? If you just do eauto, you will see that first you have to apply the rule for ht plus, right? Maybe it's useful to go through this step by step, right? So I need to show that 1 plus 1 expression has the type natural number in an empty context. So this is a plus, right? So you call ht plus, which will ht plus precisely corresponds to this rule, right? And the sub obligations are that you need to show that e1 has type natural number, e2 has type natural number. So those are the two expectation here. And then each of these are discharged through this rule, right? Which is just saying that a natural number has the type nat. So which is what we have here. So this sort of writing down things is known as typing derivation. But we don't make it explicit here because we are doing proofs here. But essentially what we are doing is typing derivation. So we appeal to ht cons to make this one go through and this also go through, right? So that solves the entire thing. Then, yeah, so just for the sake of completeness, you can also make it go through with eauto. Okay, so that's a simple one. You can also do more complicated ones here. So here is a lambda which says which takes two arguments n and m, right, and then returns n plus m, right? So I'm going to show that this particular expression has type nat arrow nat arrow nat, right? So it's a function that takes two arguments and returns this under an empty assumption, right? So you can call e constructor. There is no ambiguity here. I'm just doing it explicitly just to show that how it proceeds, right? First, you have a lambda abstraction here. So we are going to appeal to this rule here. So e constructor appeals to this rule. The thing that will happen is that we are going to extend the gamma with a binding for the binder here, right? So we are going to say the binder has the type natural number. So that's what you're going to see. So observe that this is 0, right? And when you apply e constructor, observe that n, the binder n has now been given the type natural number in this gamma, and under this gamma we are saying that this function has type nat or nat. You do the same thing again. M also goes to the binder, right? So M also goes to the environment. And under this assumption, I want to show that n plus m has the right natural number. So now you have a plus expression. So you need to individually show that n has type nat and m has type nat. You can show this thanks to the fact that both of these expectations are there in the typing environment gamma, right? So you have two sub goals. First one, you can show what is this, right? This is a variable. So what is the rule for the variable? The rule for the variable is that the variable has to have the right type in the gamma, which is what you have here, right? So if I want to show that n has type nat, then the gamma, the typing environment here, already has the type nat for n. This is what you have here. It looks it up, right? We are saying go look it up. If you simplify, you get some nat on either sides that goes through. Anyway, so the next one is also yeah, the next one is also the similar one, right? So you do e-constructor, simplify, and then equality will have made it go through, but I'm using e-constructor here, but that's fine. So you can, the other way to discharge this is you repeatedly apply e-constructor and call simplify, right? So this is just going to make it go through because there is no ambiguity. There is just, it's just going to go through and finish off things. So yeah, so this goes through. And here is an extension of that example where I just apply 7 and 4 here. So since this is a function that takes two arguments, which both of which are expected to be natural numbers, and these are natural numbers, the answer is going to be a natural number, right? So again, repeatedly applying constructor and simplify will make it go through. And here is a expression, right? This is an f applied to g applied to 7, right? Sorry, f applied to 7. X happens to happens to be an identity function. So you take this, you apply here, so you get the same expression out. So you get an identity function again, and to that identity function you apply 7, so you get 7 out. So 7 will be a natural number, right? So that's what I'm showing here, and repeatedly applying e-constructor makes it go through. Okay, this is fine, right? So this is fine. What we've done is we've shown that simple expressions have good types. But what's the whole point of adding types, right? The whole point of adding types is that we are going to say something about type safety. So what do we mean type safety? Let's make it very, very concrete. So let's switch back to the slides. Type soundness also, right? Type safety, type soundness. I'm using this interchangeably. But what do we mean by type soundness? We mean in this particular context that if you have a program in this language, in simply type lambda calculus, right, that is well typed, then they do not get stuck. What do we mean stuck, right? We say that an expression is stuck if it is not a value, but you cannot reduce it further. An example for a stuck expression is say 5 plus lambda x dot x, right? 5 plus lambda x dot x does not make sense because you cannot add 5 to an abstraction. And if you look at our operational semantics, we don't have rules that sort of tell you how to reduce that, right? We always expect. So if you look at this rule, so you will end up with values on both sides, 5 plus lambda x dot x. But here we can't make a step, right? Because it says that you have to add n plus m, the natural numbers n plus m. But this m argument here is a lambda x dot x that doesn't make sense. So this interpreter will get stuck. So what happens in real languages is that we don't operate at the level of interpreters. We've actually compiled it down to some assembly language value, right? So this might just be a pointer or a code pointer that is sitting somewhere. And you'll be adding some natural number to a code pointer, you'll just get bizarre results. Or you might say apply. So this position, you expect a lambda, right? This might be a code pointer or a closure. And if you happen to have, say, the integer 0 here, you might just try to run, you might just set your PC to 0 and then start executing, that will just segfault, right? So being stuck here corresponds to doing some very terrible things in real programming languages. Even though C has some types, right, it doesn't guarantee you type safety because it allows arbitrary casting between types, and you can get segfaults, right? But what it means here is that in a language like OCaml, which has the same notion of type soundness, you will never see segmentation fault because you are trying to apply a function where the function position happens to be a natural number 0. We will not get there because of type safety, right? So this is what we mean by stuck, right? So what we are saying is that if your program is well typed, your program will not get stuck. This is a very nice property, right? And yeah, okay. So we can formalize this, right? We can formalize this as a type soundness. What we are claiming is that if your expression has the type tau, then not being stuck is an invariant for the transition system that is obtained by the expression. A transition, this math cal t just stands for the initial state being that expression, and the step function being the step function that we define. The transition system step function is the step function that we define. So we are claiming something very nice, right? So just by giving the type at runtime, you will never encounter the stuck state. Right? This is very nice. And the way this is usually proved is by separating this into two separate theorems: progress and preservation, right? And what progress tells you is that if a lambda expression has type E, has the type T, then E isn't stuck, right? So if E has type T, then E isn't stuck, which just means that either E is a value, right, or you can take a step. So if you can type something, then it is either a value or you can always step, right? So that is progress. That tells you when you can make progress. I've made progress, but what can I tell about the resultant expression? That is what you have expressed through preservation, right? If the expression E has type T, and you can take a step, right, to E prime, E goes to E prime, then E prime also has the same type, right? This seems obvious, but if you sort of, what we are claiming here is that assume that you have some complex program that is supposed to return a natural number, right? And then you take a step, you do some reduction step. What we are claiming is that by taking a step, suddenly this expression, the resultant expression, will not have the type string, right? If the program has the type natural number, by taking a step, at every step, the sub expression, not the sub expression, the resultant expression will also have the same natural number type. This is quite important, right? So if you think about it, this doesn't happen in practice, but you can imagine, say, writing incorrect semantics, which says, if you give me 0, I will always take a step to some lambda xx, right? That particular step rule will not satisfy this preservation rule, because 0 has a natural number type, lambda xx has it's a function type, right? So what the preservation tells you is that if you keep reducing the expressions, you will always preserve the type, right? So that's what preservation is telling you. And with progress and preservation, we can actually go ahead and prove type soundness. So in your assignment, next assignment, you will prove type soundness. You will prove type soundness for an extension of simply type lambda calculus with subtyping, right? So we will have subtyping. We will have width and depth subtyping. All of that will be explained in the assignment. At this point, you should be able to sort of read the description and understand the semantics. And then what we will do is that we will actually go ahead and prove that this particular transition system that we define will preserve type soundness. So pay attention to what we are, how we are going to prove progress and preservation. The same sort of steps will apply to the one with subtyping. There will be some interesting bits because subtyping is actually a quite powerful notion. So the width and depth subtyping sort of captures what you have in object-oriented languages. So yeah, anyway, so I don't want to say more about that. You can read that in the assignment description. But anyway, so let's dive into the Coq development, right? So first thing we want to do is to define what stuck is, right? We define it as unstuck. We say an expression is said to be not stuck if it is a value, right? If it is a value, then it's not stuck. It is already done. Or there exists an E prime, which is an expression to which you can step, right? You can step from E to E prime. So that is stuck, unstuck. And we are going to sort of, we are going to do the proof step by step, right? We are actually going to not do any automation, but the automation is there later. I'm not going to talk about the automation. You can look at the automation and you will understand what's going on. But for the sake of understanding how the proof is organized, we'll just go through the proof, right? So as I mentioned, we have progress and preservation. So we will prove progress in straight away, right? Proving progress is actually quite easy. Preservation will use some lemmas, additional lemmas. We'll get to that. So how do we write progress, right? What does progress say? If the expression E has type tau, then it isn't stuck. So here is for all expression and types T, if the expression has type T, then the expression is unstuck, right? Not stuck is unstuck. So we prove it by induction on the, derivation of the hash type. So we will do induction on this typing derivation. And then we will go ahead and prove that the expression is not stuck. So unstuck is a definition. So we are going to unfold it first, and then we are going to apply induction on one. One is the first term here, right? So we are going to do induction on the derivation of typing rules. We are going to simplify and try equality. So this is going to discharge the simple ones, but all of the interesting ones will be left. Okay. So we have 4 sub goals. So if you sort of stare at each one, what is the first one saying? The first one is saying that n is a natural number, right? It is actually a natural number, and we are claiming that either the natural number is a value, or you can step from n to e prime. Obviously, you cannot reduce the natural number any further. Natural number is a value, right? So the way to prove this is we choose the left-hand side, and we have the fact that a natural number is a value. We have this fact defined earlier, which I think it's called vconst. So we directly appeal to the constructor that goes through. Okay, the second one has a lot of disjunctions, right? Because of the way we've defined the unstuck, right? It can either be a value or you can take a step. And you have 2 sub-expressions. We have 2 induction hypotheses, right? Both of which have the OR. And we also have a disjunction in the goal, right? So we are going to be left with a number of sub-goals from this. We are going to use propositional to destruct it and just do the usual stuff, right? So propositional splits it into a number of sub-goals. So it actually produced 4. So we'll look at what each one is, right? So what does it say? If you just stare at this one, so we have expression E1, expression E2, right? And E1 is a natural number, E2 is a natural number. E1's type is a natural number, and E2's type is a natural number, right? And what we are claiming is that both E1 and E2 are values, which means they must be the natural number constants, right? If they are the natural number constants, then this is an expression, right? E1 plus E2 is an expression in our language. So don't be fooled by the fact that there is a plus here. This is an expression in our language. The only values in our language are the lambda expression and constants. So this does not hold, right? But we know that both of these are values and natural numbers. So we can actually take a step here, right? This is going to be some 7, this is going to be 3. We can always take a step which reduces to the result of that, which is 10. So we are going to prove this by appealing to the right-hand side, right? And we are going to do some destruction and just convince Coq that this is the case. So we are going to choose right. Okay. There is some automation that is used here in order to maintain compatibility with different Coq versions. But the automation is sort of very, very simple. All we are saying is that, oh, look at the match the goal. So we are using match with goals here. But all we are saying is that pick the hypothesis which says value E1. Oh, there is this value E1. And the reason why we are using this automation here is that the different versions of Coq tend to name the variables differently. So the hypothesis is named as H1 here. This is a generic variable, right? So I'm just naming it as H1 here. It happens to be H3 here. So in order to avoid this confusion and to make the proof sort of robust to these version changes, so we are using the goal here. This is not necessary for a particular version. But anyway, so all we are doing here is that we call the hypothesis, which is value E1 as H1, right? And we call the hypothesis, which is hash type E1 as H2. We do have that, right? So we do have that as H here. And all we are doing is that we invert H1 first, which is this one, invert value E1, and then we invert H2, which is inverting this hypothesis. What do we learn, right? What is it that we learn? We will learn that this will be, when you invert this one, we will learn that it is either of the two values, right? Sorry, it is either of, it is either of the two values. It is either a natural number or a lambda abstraction. But we also learned that E1 is a natural number, which means that it has to be the natural number constant, right? That is what we are going to learn. So if you invert both of them, all you've done is that observe that this E1 is going to be replaced with N, which is a natural number. See, this E1 has been replaced by N, and N is a natural number. This is due to the fact that, I mean, these two facts combined, right? We know it's a value, and we also know that the value is a natural number, and the only value that is a natural number is the natural number constant. So that is why it got replaced with this natural number constant N. And we are going to do the same for the second expression as well. We are also going to learn that E2 is also a natural number constant. Cork is just going to pick some name for that, and the name it has picked is N0, right? N0 is also a natural number. Okay, that's done. So now I have to show that I can step from N plus N0 to some expression E prime. Actually, I know what this expression concretely is going to be. It is going to be a constant expression with N plus N0 as the value, right? So I'm instantiating the existential variable. I'm using the exists tactic, right? I'm instantiating the existential variable E prime here, with this expression here. So that is substituted for here, right? So that gets substituted. And now we have to show that you can make the step, right? This is the usual thing as what we had seen with evaluation contexts, right? What do you have to do? You have to pick the expression to evaluate. I'm going to pick the entire expression to evaluate. So I plug the evaluation context to be whole, right? I'm applying step rule with the evaluation context to be whole. So if you plug in some expression in a hole, you get the same expression, right? So if you plug in this expression in a hole, you get the same expression here. So that goes through with E auto. And same with the other expression as well. It also goes through. And step 0, this arithmetic, right? So this is going to be some constant N plus expression constant N0 that is just doing arithmetic, so that E constructor makes it go through, right? That is discharged. So we've discharged exactly one of the subgoals. We will just do one more, and then we will skip a few of these. So now again, look at the goal, right? So we have E1 plus E2. What do we know here? So E2 is a value. E2 happens to be a constant, right? But E1 is a some expression which is not a value. We don't have that fact here. But what we know about E1 is that you can actually take a step from E1 to E prime, right? And we know that both of these are natural numbers as well. So that is on the side. But the fact is that this expression has some constant here, right? Some value here, which is E2. That happens to be a natural number because we know that natural number, the only value which is a natural number, only value which has the type nat is a natural number. And E1 is a more complicated expression, and we can take a step on E1, right? So this is certainly not a value, but we can certainly step the whole expression, right? Because we know that we can reduce one step of E1. So just going through the motions, right? So we know that this is going to go through thanks to this fact. So let's invert this hypothesis. All we are going to do is that this existential variable becomes an arbitrary x expression, and we know that we can step from E1 to x. We invert that as well, right? And then we are going to choose the right one. because that's the thing that we are going to actually show holes. Now that we've expanded everything, we can just do E auto. Because we had previously added all of the constructors as hints for auto rule, this goes through. You can do E auto, it tells you what rules it applies. So it did existential intro, then step rule, then it picked the right way to plug the hole, and then it just went through. You can step through it in your own time, right? So that's the second one. The third one is going to be the flip side, right? Here, E1 happens to be a constant, right? E2 happens to be a more complicated expression, but you can step. So we need to show that either of these holds. This does not hold, but the right-hand side will hold. The right-hand side will hold thanks to the fact that, 1 second, the right-hand side, the right-hand side will hold thanks to the fact that we can take a step on E2. This is the same as the previous one. So that also goes through. And the fourth one, we see that neither of these are values, right? But you can step both of these, right? So, and the way, so if both E1 and E2 are complex expressions, the way our evaluation context is going to reduce it is it's going to reduce E1 first, right? So that's the reason why we invert E1 here, right? We say we pick the hypothesis where it says step E1, and we invert that hypothesis, which inverts this hypothesis here, right? So if you do that, then you get a step on that. We invert that as well, right? And then we pick the right one. That's done. So if you observe this, so you can, so there is E1, right? E1 is actually, if you plug C with E0, you get the E1. And if you plug C with E3, you get X. And you can step 0 from E0 to E3. So you can take a smaller step here, right? And what are you going to do what are you going to get as a result? You're going to get this particular E1, right, is going to reduce one step, and you're going to get X here. Thanks to the fact that step 0 itself gives you an E3, and if you plug E3 into the same context C, you're going to get an X. So I'm going to instantiate this existential variable with plus X E2. That's the result of doing one step. So that's why I'm plugging this existential variable with plus X E2. Okay, now that is done. This is a complicated expression, right? This is a complex expression which I'm reducing. So the whole, I'm going to pick the whole on the left-hand side, which is precisely plus 1 C E2, right? I'm going to call step rule with reducing on the left-hand side expression. So rest of this will just go through directly. So this is just the E constructor. So I'm just going to pick, so there is a C, there is a E1 here, some variable here that gives me E1, and that is going to be E0 here, because that's the one that we have in the assumption. So if you look at this variable, this unification variable, that is going to be unified with E0, thanks to this fact, right? Oops, that not happened. Okay, it happens here. Yeah, so it converted to E0 here, and the same with the other one as well. So you pick the E constructor. I'm using E auto here, but so so the rest of the thing goes through, right? So goes through, and then this got replaced with E3, and you have this hypothesis here. So all we are saying is that you can step this one, right? Thanks to the induction hypothesis. I am actually not going to cover the rest of these rules because these are very, very simple. So use the same principles, right? So, so if you sort of go through this in your own time, you will find that this is applying the same sort of reasoning. So you invert the right hypotheses to get the facts and show that you can take a step. There is no left rule. You can always take a step. Go through it in your own time. It's not that complicated, so I'm not going to explain it in detail. But yeah, but it has the same sort of reasoning. And what we've done here is that we proved progress, right? We've shown that if you can give the type t to this expression, then e is either a value or you can take a step. So that's what we proved, right? So tomorrow in the next class, right, when after we cover the midterm solutions on Wednesday, what we are going to do is we are going to see preservation. So preservation requires a few more steps. All of these are sort of intuitive. If you look at it, we just have to go through these motions. And then using progress and preservation, we will actually show type safety. Just that unstuck is an invariant for that program. So the what we are claiming is that the program will not get stuck. So we will do that in the next class. Again, the reason why I'm doing this in such detail is that this is exactly what you will need to do in order for solving the next assignment. Anyway, so I'll stop here. We'll catch up on Wednesday. So there is no class tomorrow. We'll catch up on Wednesday. Thanks everyone. Bye bye.